Okay, so today we're going to talk about another integration technique that's called trigonometric substitutions. The idea behind this section is to use right triangles along with the Pythagorean theorem to simplify some more difficult integrands. So let's look at an example and then we'll summarize what it is we're doing. We're starting off with the integral of 1 over the square root of 4 plus x squared. Now, this doesn't look terribly complicated at first, but I want you to notice that right now we don't have any other way we can integrate this. It's not an arcsine or arctan or any of those. We can't do a u substitution, so we need some other technique to figure this out. So what I want you to observe is that this is in the same form as this triangle I have drawn. So the hypotenuse, if we think about a as 2, that square root of 4 plus x squared is the same expression I have in the integrand. So take a look. Theta is the angle, 2 is the adjacent side, x is the opposite, and then by Pythagorean theorem, this becomes the hypotenuse. So what we want to do is come up with some expressions for everything that's in this integrand in terms of trig functions using SOHCAHTOA and the triangle. So notice that secant theta would be equal to the hypotenuse over the adjacent side, and that means that 2 secant theta is equal to the integrand. Now I chose secant because it only involves the hypotenuse and a constant as opposed to this opposite side with x. Now the other replacement I need to make is I need to come up with an expression for dx. So the way we're going to do that is we're going to come up with an expression for just x. Think about, in this triangle, if I wanted an expression in terms of x, which trig function would be easiest to do that with? Notice that tangent theta is opposite over adjacent, which means that 2 tan theta is equal to x. Now in the integrand, I want dx, not just x. So what we're going to do is we're going to take the derivative of this expression. So the left side becomes 2 secant squared theta d theta. The right side just becomes dx. So go back to your integrand and make some substitutions. So the denominator, which was the hypotenuse, turned into 2 secant theta. The numerator, which was dx, turned into 2 secant squared theta d theta. We're going to simplify this a little bit, and we're just left with the integral of secant theta d theta. The integral of secant theta is the natural log of secant theta plus tan theta. Now remember, we were integrating in terms of x, so we have to go back and change this expression in terms of x. So I'm going to replace secant theta with what we said it was equal to here, and tan theta with the x over 2. And we're almost done. There's one extra step I want you to take here because of the natural log. Write that all over 2. And remember, with log properties, we can separate this into the natural log of the expression in terms of x minus the natural log of 2 plus c. And remember, when we have an extra term that's a constant out there, we can just combine that with the c. And this is how I want your final answer. So this technique is called trig substitution, and there's 3 main forms of the right triangle that we're going to work with. The first one is the one we just looked at. So if the integral contains the square root of a squared plus x squared, that's going to be your hypotenuse. X is going to be your opposite side, and a is going to be your adjacent side. Always put your theta in the acute angle in the lower left side of the triangle. On the other hand, if we want the square root of a squared minus x squared, move the a to the hypotenuse, put the x on the opposite side, and then your adjacent side becomes that radical. And the last form we're going to work with is if we want the square root of x squared minus a squared, move x to the hypotenuse, leave a as the adjacent, and then the radical becomes the opposite side. This is a really important page. Either print it out or make sure you write all three of these forms down with the pictures, because every time we set these up for consistency, I want you to use one of these three forms. So let's look at another example. So now we have the integral of x squared over the square root of 9 minus x squared. And again, I want you to observe that this is not an inverse trig function. It looks similar to arcsine, but it's got that x squared on top. It's not a u substitution or any of the techniques we learned last year, so we're going to do the triangle. So since we have the square root of 9 minus x squared, that means that 3 is going to go to the hypotenuse, x is the opposite side, and the radical is the adjacent side. So we need an expression for x for sure. So let's start with coming up with an expression for x in terms of our triangle. Sine of theta would be opposite over hypotenuse. So that means that 3 sine theta is your x. Now in all of these problems, we need an expression for dx. So once you get the x expression, you're going to take the derivative. And in this case, dx is 3 cosine theta d theta. So you're always going to need to come up with an expression for x, at the very least, because you're always going to have a dx. And in this case, we also needed the x in the integrand. We also need to come up with an expression for the radical. So if we use cosine theta is the square root of 9 minus x squared over 3, adjacent over hypotenuse. Or the radical just turns into 3 cosine theta. Now if we go through and make some substitutions, the x squared turns into 9 sine squared theta. The dx turns into 3 cosine theta d theta. And the radical is just 3 cosine theta. And if we're lucky and we've done this right, we should have something we can integrate once we simplify it. So I pulled the 9 to the front, and remember when we integrate sine squared theta, we're going to use this formula, 1 minus cosine 2 theta all over 2. So I put the 9 halves in the front. And then if I do a little u substitution, this becomes 9 halves theta minus 9 halves times 1 half sine of 2 theta plus c. Whenever you do these, you have to remember to go back and put everything in terms of x. So the theta is a little bit different here. Think about how could I take this expression that's in terms of x and get an expression for theta, or this expression. So since sine theta was x over 3, how could I get theta by itself here? We're going to use arcsine. So theta is going to turn into arcsine of x over 3. Lastly, I need an expression for sine of 2 theta. I don't have an expression for sine of 2 theta, but remember that sine of 2 theta is the double angle identity, and that can be written as 2 sine theta cosine theta. And I do have an expression for sine theta and for cosine theta from up here. If you go through and make those substitutions and do a little simplification, you should get this as your final answer. Take a minute, make sure you see all of those substitutions. Sine theta was x over 3, cosine theta was the radical over 3, and then with a little simplification, we get this. Before tomorrow's class, please go back to the previous slide and make sure you have memorized the 3 forms of the triangles that we're going to use for all of these problems. It'll make your life a lot easier.